Hi, Bobcats. Reaction stoichiometry is the group of calculations that we do around the amounts of reactants and products in a chemical reaction. Before we launch into the reaction stoichiometry, I just wanted to remind you of something that we've already learned. We have learned that 1 mole of a substance is equivalent to 6.02 times 10 to the 23rd representative particles. I usually abbreviate those with an RP. What happened to my pen? There we go. There's my RP for representative particles. If the substance is a gas and it's at conditions that are called standard temperature and pressure, which are 0 degrees C and 1 atmosphere pressure, then that 1 mole has a volume of 22.4 liters. And if we were to take that 1 mole and weigh it, we would find that the mass of that 1 mole has a weight equal to the molar mass, which we calculate from the periodic table using the subscripts in the chemical formula. So we've spent some time working on mole conversions where we just take a single sample of a substance and we convert it between grams, moles, particles, and liters. This is going to be just one piece of our new reaction stoichiometry calculations. And we're going to be using these mole triangle conversions to convert the units of our sample. So, reaction stoichiometry. These are the calculations related to the amounts of reactants and products in a chemical reaction. We absolutely must have a balanced chemical equation in order to do a reaction stoichiometry calculation. And we are going to interpret the coefficients in our balanced equation as showing us the amounts of our reactants and products in terms of moles. If a coefficient is not written, it's understood to be a 1. Moles is the standard interpretation when we do reaction stoichiometry, but I just wanted to point out, because sometimes it's shorter and quicker to do calculations, we can also interpret the coefficients as showing us the amount in terms of representative particles, which for this particular reaction would be molecules. Right, so these coefficients also show the ratios in terms of molecules or representative particles. And if everything that we're talking about is a gas, also in terms of the volume. So we typically talk about these ratios as if it's all about moles, but it also can be molecules and volume. There are many different problem-solving techniques for doing reaction stoichiometry. I'm going to just show you 2, but there certainly are more than that. There is a standard American way of solving these problems. This typically involves more steps than other ways because we tend to break down the problem-solving process into small steps, and then we have to put all of those small steps together, and we end up sometimes with kind of long calculations. It's an extremely powerful technique because we can easily expand it to solve all sorts of other problems. For instance, when I teach General Chemistry 2, towards the end of the semester, there's an electrochemistry problem where we end up stringing together maybe 8 of these conversions all in a row to solve the problem. So it really has a lot of application, and it's something that can easily be extended. This approach is what you've probably seen if you already have some experience with stoichiometry problems. I'm also going to show you an alternative approach that I developed after having some really interesting conversations with another chemistry instructor at another institution. She was visiting in the United States for a short period of time, a couple years, and her regular job was teaching at a university in France where she taught university students how to be high school chemistry teachers. And we had a lot of interesting conversations exploring the different problem-solving approaches in France versus the United States. And what I'm going to show you is not what they do in France, but it's kind of a hybrid of the approach from France and dimensional analysis. So in France, they tend to do the problem solving more in terms of ratios, whereas we tend to string together these dimensional analysis conversion problems. So I'm going to build off of the ratio approach and turn it into a dimensional analysis approach. Both of these ways are solid problem-solving approaches. You should work with whichever one really works for you. And if you learned how to do stoichiometry with a ratio approach, by all means, use the ratio approach. As long as you consistently get right answers, any of these approaches are great problem-solving approaches. So this slide is going to end up being our big idea slide. This slide is going to lay out the thought process behind the nitty-gritty mechanical, mathematical stuff that we're fixing to do. So if we have a balanced chemical equation, nitrogen plus 3 hydrogens give us 2 ammonias. The traditional American way of working these problems is to interpret those coefficients as moles. This equation is telling us 1 mole of nitrogen reacts with 3 moles of hydrogen to give us 2 moles of ammonia. Based on those 3 quantities, we can build a conversion factor that converts moles of one chemical into moles of a different chemical. That's great. That's all I need to explain for building our conversion factors for the traditional American way. Everything else we're going to tackle, or we're going to tack on to our problem solving in the traditional way, is going to be a mole triangle conversion. So that's all we need for the traditional way. But for the alternative approach, I'm going to do a little bit of mathematical manipulation here. What I'm going to do is take these 3 quantities and factor out the coefficient. If I factor out the coefficient, what I have left is the coefficient times 1 mole of the chemical. Well, we know from our mole triangle and mole conversion problems that 1 mole is equivalent to the molar mass in grams for each chemical. So for each one of these chemicals, I'm going to substitute in its molar mass in place of 1 mole. So I now have 1, which is the coefficient, times 28.02 grams of nitrogen, 3 times 2.02 grams of hydrogen, and 2 times 17.04 grams of ammonia. So all of these things are equivalent because I just substituted in the molar mass. The next substitution I'm going to do is I'm going to substitute the molar volume of a gas, 22.4 liters. And the final substitution I'm going to do is to substitute in Avogadro's number of representative particles. Since these are all covalently bonded compounds, the representative particle is a molecule for all of these, and MC is my weird personal abbreviation for molecule. So we have now written on this page a whole bunch of expressions that are all equivalent to one another so that we can do any sort of conversion that we need by picking any 2 of these equivalents because they are all all of these things are equivalent. So we can build our conversion factors. Down in the bottom, we want to match the units of what we already have. Up in the top, we want to match the units of what we're trying to find. And we can pick any two of these things. If we're using the shorter approach, the alternate approach, the way we're going to build these equivalents is by taking the coefficient from the balanced equation times a quantity off of the mole triangle. Roughly speaking, throwing the coefficients in here is going to change the chemical. That's going to be our conversion factor for changing from one chemical to another chemical. And then whatever quantity we threw in off of the mole triangle is working on changing our units. I'm waving my hands a little bit here, and it doesn't strictly break down that way, but taking the product of the coefficient and the quantity from the mole triangle in relation to the second part where we take another coefficient and another quantity from the mole triangle, those combinations are what really change both the chemical and the units simultaneously. All right, just to compare and contrast these two techniques, in the traditional way, the first fraction we're going to write is whatever we are given, the number, the unit, and the chemical over 1. The second fraction we're going to write is taking whatever we were given and converting it to moles if it was not already in terms of moles. That's going to be a mole triangle conversion. That's why I put the little triangle by number 2. The third conversion factor we're going to write is going to be based off of the coefficients in moles. And the fourth conversion factor is where we're going to convert moles of the chemical we just found to the units that were wanted for that chemical. Going the shorter approach, the alternative way, we're going to start exactly the same way. So these two things are exactly the same. And so the first fraction is going to be the same no matter how we set it up. But then with the shorter way, the alternate way, we are going to just build one more fraction. That conversion factor down in the bottom is going to have the coefficient times a number from the mole triangle, and the top is also going to have a coefficient times a number from the mole triangle.